So there we go. How about now? Now you should be able to hear me. So anyway, good morning. Glad you guys could join me. If you're not watching it live, I encourage you to watch it live. I don't think 9 o'clock is too early in the morning to do that. But anyway, here we are. This morning we're going to go over the bell work from Friday, which would have been the 17th of April. It's a pretty good bell work to go over because it covers a lot of the things I know you guys are struggling with. And I know because a couple of you have emailed me and said, I have no idea what I'm doing. And then you didn't give me like any context. You just said, I don't get it. So we're going to go over this bell work. I hope that'll be helpful. After that, we are going to talk about the equilibrium quiz. And then after that, we'll have Q&A, just like normal. I hope you guys can hear me okay. I'd had my mic muted and I forgot. I thought I could do this screen, and this screen would automatically mute my microphone, but it doesn't seem to be working. But anyway, I'll figure it out. So anyway, let's just get right into it. So here we go. This is the bell work again. This is from last Friday, and this will be the last bell work that you guys have on bell work number 5. So this will be the last box. A lot of you are getting a lot better at how you submit your bell work, where you're actually going in, and if you do it on a piece of paper, great. Take a picture of that, put it in the bell work box for that day. I don't want to call on any particular people because I don't want to embarrass them, but some of you, you know who you are, doing a fantastic job. Please keep doing that. And if you do try and write with your finger, please make sure I can read it. No offense to anybody, but you probably know who you are too. So anyway, here's how bell work. It says balance the formula above. And the reason we have to balance it is because the very next problem, question number 2, says write the KEQ expression. And as you hopefully know, you can't write that KEQ expression unless you balance it first. So we'll go ahead and balance it, and we'll see what we get. I am going to make a list. I always do. I'm going to make it upwards above the arrow this time because I didn't leave myself enough room. But we got one carbon over here on the left. We got a carbon over on the right. We have 2 H's on the left. We have 2 H's on the right. We have 1 O on the left. We have 2 O's over on the right. So we do have a little bit of work to do. Shouldn't be that confusing. First things first, I think what I'm going to do, I'm going to put a 2 right here. If I put a 2 in front of H2O, 2 times 2 gives me 4 H's. Okay, so we have 4 moles of hydrogen on the left side. 2 times 1 oxygen is going to give me 2 oxygen. So as you can see, I've now fixed my oxygens. They're what they should be. The hydrogen's not happy, but that's okay because it's by itself over on the right side. So 2 times 2 is going to give me 4 hydrogen. So as you can see, now everything's balanced. Now we can start to do something with this. So now we get to problem number 2. Problem number 2, it says write the KEQ expression for the formula above, and I guess I'm going to do it just to the right over here. I should have enough room. Now remember, I hope you remember, products over reactants, products over reactants, products over reactants, products over reactants. Okay, you've got to remember that because that's half the battle. My wife and I were talking about it this morning, that one of the things that students struggle with these particular types of problems is they try to do reactants over products. That's not it. And I know you want to because you want to read it from left to right as you go across that problem, but it's still products over reactants. That's just how it works. So I'll say, all right, well, KEQ, products first, all right? So I have H2, and I'll go ahead and put the states in there. That's going to be important here in a second. So I'm going to put the state, that is gas, that's hydrogen gas. But because it has a coefficient, if you don't know what I'm talking about, here's that coefficient. Because it has a coefficient of 2 in front of it, that means that I should put a squared on that. So I'm going to put an exponent of 2. My other product, my only other product, is CO2, which is also gas. Okay, but it does not have a coefficient in front of it. Okay, see, there's nothing there. All right, and so because of that, I'm just going to leave it alone. Now on the bottom, I'm going to put H2O because it's a gas, and it has a coefficient of 2. All right, see, 2 here becomes the exponent down below, and I am not going to put solid carbon. as I've told you guys a couple of times, whenever you're doing a KQ expression like this, you're not going to do any liquids and you're not going to do any solids. All right? You only do gas and aqueous. Those are the only things that go in. And the reason is, if you take, I think my example last week was I said if you take sand and you take salt and you mix them together, you just get a mixture of salty sand. No chemical reaction is taking place. It's not that the salt is bonding with the sand or the sand is bonding with the salt. They just mix together. And then obviously if you tried really hard with, I guess, tweezers, you could separate it all out if you cared to. But if you have liquid water, okay, and then you have liquid oil, you put the two together, they're just going to mix up. They're not reacting. Okay, they're not reacting. That is not a reaction. So here, a gas, okay, and another gas, they can react together. And so that's why we're going to put them in the KQ expression. So anyway, number 2, done. Number 3, how would the reaction shift? So this is the thing I think a lot of you are struggling with. This that we just did, right in a KQ expression, it's not that bad. Products over reactants, et cetera, et cetera. But Le Chatelier's principle, which is what number 3 is all about, seems to be confusing some of you. And honestly, guys, because I can't meet individually with all of you, I can answer questions via email or remind or whatever, but because I can't meet with all of you, it makes it a lot more difficult, okay, to teach this. So you're going to have to do the best you can, and that includes copying the notes. And as you write them down, please, 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 don't just be sitting there going, okay, I'm just writing other notes. And while you're doing that, you're watching a show or something. That's not going to help you. Focus on what you're doing and think about what you're writing. Don't just copy it down because as of right now, I'm not grading your notes. If I feel like I have to, I will. But the notes are for you, so take advantage of it. So I do have notes on Le Chatelier's principle that talk about how everything impacts something else. So if you do increase pressure, what does that do? And that's all in the notes as concisely as I can give it to you. So anyway, left or right, or not at all. Sometimes nothing will happen. So let's take a look at this. A, increased concentration of CO2 gas. So based on what I see on my screen, I can see that CO2 is on the product side. And so you've got to think about it this way. If I increase the concentration of CO2, well, then it's going to go back towards the reactant side in order to bring everything back to equilibrium. Okay, I'm gonna say that again. Okay, think about it. We got our reactants over here. Maybe it's H2O and carbon on the left side, and on the right side we have hydrogen gas and carbon dioxide gas. So if you increase the concentration of carbon dioxide gas, see, they're not at equilibrium anymore. Okay, and so what will happen is if you increase the concentration of CO2, well, then it's gonna flow back over, okay, towards the left until it brings everything to equilibrium. Okay, so the answer to number 1, or sorry, A, is going to be it's going to go to the left. I'm not going to do this in green. Let's do it. There we go. It's going to go to the left. All right, let's check on some things. Make sure it's working. It looks like I only have one person watching. I hope that one person will tell me that they can see and that you can hear me and what I'm doing. I think you should. Next one, B, decreased concentration of H2 gas. So this is the opposite. Instead of increasing something, now we're decreasing something. We're still on that right side. We're still on the products side. So if you decrease the concentration of H2, well, then it's going to flow that way in order to bring everything back up again. All right. So if you decrease the concentration of that, it's going to flow that way and bring until everything comes back to where it should be. So if you decrease H2, the reaction is going to try and produce more H2 to bring it back to equilibrium. So it's going to go to the right. So when we're saying left and right, it doesn't mean the reaction is actually moving. It doesn't mean that all the reactants move from the one side of the beaker to the other side of the beaker. That's not what I mean. When I'm saying left and right, I'm referring to this whole reaction. So this is the left side over here. All right, here's the right side over here. So the right side is the products. The left side is the reactants. So if I say, when I'm telling you it goes to the left, okay, which I hope I'm pointing left. We had an issue with that on Friday. But if it's going to the, or Thursday, whenever. If it goes to the left, what I mean is it's going to form more reactants. It's going to form more H2O gas. It's going to form more, carbon solid, whatever. But that's what I mean. If I say it's going to go to the right, then that means it's going to form more of the products until everything comes back to whatever equilibrium position it should have. All right. C, decreased the concentration of solid C. Okay, just like I said, and you can see it's in red over here, okay? Liquids and solids do not matter. The same is true when you're dealing with equilibrium. Because if you decrease the concentration of solid carbon, it's part of the reaction because that's where you're getting the CO2 gas. But for the most part, if you decrease and take away solid carbon, that's not really impacting the equilibrium that much. Now, yeah, it could change a little bit, but it's really not changing it that much because it's not actively participating in the reaction. And so, if we decrease concentration of solid carbon, I would accept it. If you said none, okay, if you said none, I'd give you credit because I'd be like, yeah, it's a solid. It's probably not going to do a whole lot. But in terms of reactants, if you think about, oh, well, I decrease the amount of solid carbon, well, that means everything's going to flow back that way to get more carbon. So it's going to flow that way to try and bring everything back to equilibrium. So you could have said to the left as well, or none, and I would have given you credit. Let's be honest, we're dealing with introductory chemistry, so one way or the other is fine with me. Next, we go to D. All right, D and E are the most challenging on this problem because it requires you to think about gases, and it requires you to think about what pressure and volume actually mean. We have actually not gone to that unit yet. It's coming soon. In fact, I think is it the next unit? I'm not going to look right now. But it's coming soon. We'll start talking about heat, pressure, volume, and gases and all that stuff. But for now, think about pressure as being, a container pushing in on something. Okay, that's pressure. Or other molecules pushing on other molecules. It's all about a push. Pushing on something else. Volume is obviously just size of something. So here's 1 liter, all right? That's a certain amount of volume. But if I all of a sudden were able to squeeze this and make it so it occupied less volume, we need to think about what that means in terms of a reaction like this. So for D, think about my line of thought here. For D, if you increase the pressure, okay, probably what that means is you're going to decrease the volume. Now, I know the problem doesn't say anything about that, but think about it. If you increase pressure on something, if you squeeze something together, aren't you probably going to make it go smaller? Aren't you probably going to, make it so there's less room to move around? And so if there's less volume, it means there's less room for gases. And so what that means is it will shift to the side with less moles of gas. Okay, so that's my line of thought. Okay, it's just logic. It's you thinking and saying, all right, well, I increase pressure. If I make it so there's more pressure, that means there's going to be less volume. There's going to be less space. If there's going to be less room for gases, that means it's going to shift to the side with less moles of gas because there's less room for gases to move around. So if we look at the problem, I can see I have 2 moles of gas on the left side. Okay, see, 2H2OG. That means there are 2 moles of water vapor, which is gas, water in the gas form. There's 2 moles on the left side, but on the right side, look, we have 2 moles of hydrogen gas and a 3rd mole of carbon dioxide gas. So there's more moles of gas on the product side. And so because there's less room for gases to move around, it's not going to shift to the side with all that gas that wants to float around. It's going to shift to the side with less moles of gas. So in this case, it's going to shift to the left because there's only 2 moles of gas, and on the other side, there's 3 moles of gas. So it's going to shift to the side with less moles of gas because there's less room for the gas to move. Now we go to E, decreased the volume on the system. So when you're decreasing the volume of a system, it's just like what I was saying a second ago. You've got to think about it as there being less room for gases to move around. So really, this is the same as what we just discussed, except all I'm going to do is I'm just going to skip to this part where I just say, look, you got less volume. Hopefully it'll sync here in a second. I've already written and it's not loading yet. But if we have less volume, if we have decreased volume, that just means there's less room for gases to move around. And so it's going to shift to that side with less moles of gas. So once again, if there's less room to move around, it's going to shift to the side with less moles of gas. Why is this not syncing? I told you to do something. Anyway, it'll load in a second. So the answer to E is it's also going to be left, just like D. It's going to be the same as question D. It's going to go to the left. All right. Now we go to F. If you increase the heat on the system, So increasing heat on a system is going to be the same as kind of what we did for problem A and B. We're going to treat heat as being one of the reactants. So if you increase the heat in the system, that's like saying, oh, well, I've got more heat over on that side. So if I have more heat over on that side, it's going to shift to the left to bring everything back into equilibrium. So again, I know the hand thing may not help some of you. It's the best way I can think of to explain this to you, but that's how I think about it. I think about it as, oh, well, I lift up this side. If there's more heat, look, they're not equal anymore. So some of the products are going to have to shift back into becoming reactants. They literally do become that. So they form more reactants and go back to the left side to bring everything back into equilibrium. So you increase the heat of a system, you make it so there's more heat, it's going to shift to the left until you bring everything back to equilibrium. Okay, it's going to bring everything back to equilibrium. All right, I'm going to figure out why it's not syncing because I've never had this issue before where it takes this long for something to load. What is going on? So anyway, if you're in the chat, we're at a good stopping point for a second while I figure out why this isn't loading. Let me know what's going on. Hopefully you can see it. Hopefully you somewhat understand it. I wish there were more people because I do like to poll the class and ask you guys, oh, okay, what happens? Hey, look, it loaded miraculously. All righty. Excuse me. All right, so now that we're all caught up with our bell work, there's no one here to ask me questions because you guys can't get out of bed at 9 o'clock in the morning. Too bad, so sad. But now let's go ahead and take a look at this equilibrium quiz. All right, so we need to look at the equilibrium quiz. And the thing is, a lot of you are not going to do the equilibrium quiz because you're going to say, oh, I don't know how to do it. But those are going to be the same people where you're not looking at the videos. I'm making these videos for your benefit. It is not for me. Although I do enjoy it a little bit. I like figuring out how to use this OBS software because it's kind of cool. Other than that, it's not for me. It's for you. So here we go. Unit 5, equilibrium quiz. Answer the following questions using the equilibrium reaction below. First things first, whenever you see a chemical reaction, please check to make sure it's balanced. So I can look at this. I can see there is a coefficient in front of the Cl on the left side. So that chloride ion, it says there's 4 moles of chloride ions, which are aqueous. So that means they're dissolved in solution. So if there's that 4 in front of it, that tells me the whole reaction is probably balanced. I can see there's a 6 in front of H2O. So yeah, it's probably been balanced. It's still a good idea to check. You don't want to do the next problem, the very first problem, until you know that it's fully balanced. So anyway, number 1. Give the KEQ expression for this reaction below. So KEQ, I've told you, it is products over reactants. It's always products over reactants. So I'm going to say, all right, well, KEQ, hopefully it'll load instantly this time. Yay, it's doing it. It's going to be products over reactants. And if it helps you, write that. Write that first and just say, well, it's going to be products over reactants. If that helps you, please do that. And so I'm going to look and say, oh, well, here's my product side over here. So let's see what products we have so we know where to put them. Oh boy, it's loading slow again. Be right back. I need 30 seconds. Ooh, look at that. High tech. Not sure what's going on here, guys. If you've watched videos before, you know I usually don't have issues like this, but right now I'm writing and it's not showing up. It has a huge delay to it, so I don't know. I don't really know what's going on right now. Sync this notebook, please. Are you syncing all the other notebooks? Stop doing that. Well, we're gonna figure it out. It's gonna be okay. I'm gonna write and hope that it loads here in a moment because this is not ideal. All right. Well, anyway, products over reactants, and hopefully it'll pop up here in a second. So the first product that I'm going to write down on the top part of my fraction is I'm going to say, okay, this cobalt chloride, and so it's going to be CO, Cl4, and it has that 2- above it. Don't get too freaked out by that. Just know that it is something that we want to include. And this is aqueous. So I am going to include it in my KEQ expression. See, now all of a sudden it loads. I don't know what to tell you. It does not have a coefficient in front of it. You can see there's nothing in front of COCl4, and so I don't need to put an exponent on it. And that's it. And so if you're at home and you're saying, well, now we got to put H2O in there, because that's a product too. That's 6H2O. But guys, it has an L next to it. And so if it has an L next to it, I am not going to write it in my KEQ expression. I'm not going to do it. So don't. All right. So next, I'm going to look at my reactants. Reactants go on the bottom. Okay. I can see one reactant is cobalt, which I guess is hexahydride, but we don't care. So we have cobalt, which is H2O with a 6, and it has that 2+ on it. And great, it's not loading again. Fantastic. I'm looking at this term right here, COH2O6 with a 2+. That is one of the reactants that needs to go onto the bottom of our KEQ expression. So I'm going to put that down there. It does not have a coefficient in front of it, and so because of that, I'm not going to put one. I'm just going to leave it the way it is. But there's another reactant that I have to put on the bottom, and it's this Cl right here. So I'm going to put that on the bottom as well. Cl-. And I'm going to put a 4. The reason I'm putting a 4, there is a 4 coefficient in front of it, and so I'm going to end up putting a 4 above it in the brackets. Okay, so we have a Cl- with a 4. There we go. And like I said, hopefully it'll load in a second because this is ridiculous. I'm not getting angry, but it is frustrating. The fact that I'm telling you guys that you should be able to see something and you don't see anything because it's not loading. No idea why, because it should be there. I'm looking at it. I'm just waiting. I'm just waiting for it to load and do what it's supposed to do, guys. I don't know why I'm having issues today. See, there it is, but now I've already finished talking about that like over a minute ago. So anyway, this is the full KQ expression. You can see some of the things I'm excluding. In fact, I kind of wish I'd put states next to all of them. I think I'm going to fix that real quick. So you can see what I added and what I did not add. I'm not going to add heat. Heat is not aqueous. It is not a gas. It is not anything as of right now. So we don't add that in our KQ expression. But I am going to add this COH2O with a 6 because it is aqueous. So yes, I do want to put that in my expression. It is not going to have an exponent because, okay, it doesn't have a coefficient in front of it. There's nothing in front of CO over there. Next, I'm going to put Cl-, which is aqueous, and I'm going to put a 4 above it. Because it does have that coefficient of 4 in front of it. So as you can see, products over reactants. And I usually will not write that fraction right there that says products over reactants. That is only for you guys. So if you really feel like it helps you, you go right ahead and write that. I am not, because I don't find it useful. Okay, but I'll usually just write that. Let's look at number 2. If the concentrations are this, this, and this, and no, I'm not going to read all that junk out because it'll just be confusing, but it tells you what all the concentrations are, determine KEQ for this reaction. Excuse me. All right, so what that means is this COH2O6 is one of the things I want to know, but I'd rather do it in order of the way things are in this expression. Okay, so first things first, let's take a look at this. Let's take a look at this part of it. There we go. That looks beautiful. This COCl4 2 minus. Let's see where it has that information. Here it is, right here. It's giving me the number. It says it's 0.60 molar. So we're literally just plugging and chugging at this point. Okay, so I'll say, all right, well then KEQ is going to be equal to, on top, 0.60 capital M. And I know we haven't talked about this yet. It's coming soon. Capital M means molar, which I'll remind you guys, that just means moles per liter. There are 0.6 moles of this substance in 1 liter worth, in this case, of water. All right, so moles per liter. Don't ever think it. Next thing I want to look at, because I'm going in terms of this reaction up here, let's take a look at this. Okay, COH2O6, and I can see that they do give me that information. It's right here, and they're telling me it's 0.50 molar. So this is going to go on the bottom of this fraction. I'm going to put it right here. Okay, so it's going to be 0.50 molar. Okay, no exponent. Next thing I'm going to look at is the Cl minus. All right, I don't have a marker for this, so instead I'm just going to box it like that. So this part of it that I want, please load. Don't be dumb. But the Cl minus, they do give us that information as well. It's the 0.25 molar. And so I am going to put that on the bottom of my fraction. And don't forget that exponent. We have an exponent of 4 right here. And so don't forget to put that even when you're doing the math and putting it down below. All right? Don't forget that. I am really upset with the way things are going this morning, guys. I don't know why. I don't know why it's deciding to be like this. Never had this issue. And now, see, it's not syncing at all. It's not doing anything. Whoa, whoa, whoa. Do not close the... Whew. Well, that was not good. Well, guys, what just happened is in my haste to get the notebook to load, I closed the whole thing on accident. That is what we call a misclick. I'm very upset about it. Shoot. Let's see if it's still there. All right, there we go. All right, I got it back. I'm just annoyed. Okay, let's try that again. Here we go. Got it back. All right, so now we know where everything is. I'm going to plug it in my calculator. And all I can do is apologize. I don't know why this has been dumb this morning. It has been a tragedy. So what I'm putting in my calculator, you can do it a couple of different ways. I think it's easiest actually to start in the denominator. So I'm going to start by doing 0.25. This is exactly what I'm putting in my calculator. 0.25 to the 4th, enter. Okay, this is my way of doing order of operations, so it makes sense to me. So I'm going ahead and doing 0.25 to the 4th, enter. I'm going to go ahead and multiply that by the 0.5, which is also in the denominator. Hit enter. And then what I'm going to do is I'm going to do 0.6 divided by second answer. Okay, so I'm doing this. I know you guys probably can't see that at all, but I'm doing 0.6 divided by that, and I end up getting 307.2. So I get 307.2. Okay. There we go. Now, 307.2, you're probably asking, well, Mr. Aaron, doesn't that need to have units next to it? Not really. Whenever you're dealing with K constants, like KEQ over here, it's not going to have units because, as you can see, we have molar on top, the capital M's on top, and we have the capital M's on bottom. And so it's easier to just think of it as saying, yeah, all these M's are going to cancel, and so we don't have any units at the very end. So we get 307.2. Okay, 307.2. So look at number 3. Good gracious. For each of the following changes to the system, explain which direction the reaction will shift. So this is the Le Chatelier. This is the stuff that you guys are struggling with because you don't seem to understand what this stuff means. So look, problem A, more of this COH2O6 is added to the system. So once again, I'm looking at the reaction. I'm saying, oh, well, that is one of the reactants. It's on the left side of the equation. COH2O6 is over here. So think about it. If I add more of this, it is going to want to shift until you bring everything back to equilibrium. So look, if I put more COH2O6, it's going to want to go that way and form more products to bring everything back to equilibrium. So if I add more of this cobalt, I don't know, I guess it's hexahydrate. If you add more of this cobalt substance, then it's going to shift towards the right to bring everything back to equilibrium. It's going to go to the right to bring everything back to equilibrium. So that's my answer here. So remember, at equilibrium, it does not mean that the amounts are all equal. It means that the rates are all equal. Okay? So if we have a certain amount of this cobalt water compound, and maybe at equilibrium there's 1 mole of it, or 1 molar of that, and maybe at equilibrium there's 1 molar of chloride ions, okay, or 4 moles rather. So if it's 1 to 4 at equilibrium, then we'd say, oh, well, if I add more of this, that's more than it should have. And so what we'll do is we'll shift the other way until we bring everything back to that same concentration. So that's really what's happening. So when I say right, and I'm not going to make you guys explain it, if you can understand it goes to the right because you have more on this side, so it's going to form more more products to bring everything back to equilibrium. That's good. But really what's happening is it's forming more products to bring everything back to equilibrium. So it'd be forming more of this cobalt chloride over here on the right side. It would form more of that to bring everything back into balance again. Let's look at B. Cobalt chloride is removed from the system. So this is the opposite, but it's also on the opposite side. So instead of saying, oh, well, I'm going to add more of something, no. We're taking away something. And so look, as I take things away, it's going to want to flow that direction to bring everything back to equilibrium. So if I take away this cobalt chloride, it's going to want to go to the right to bring that back up again, to bring everything back to equilibrium levels. So this one is still going to be going to the right. It's still going to be going to the right. All right. C, the system is heated. All right. So heat. We didn't care about it when we were doing the KQ expression. We do care about it now. If you add heat to the system, it's just like what we were doing in problem A. If you add more of this cobalt hexahydrate, if you add more of that, well, we're adding more heat now. So once again, if you add more heat to the system, it's going to want to go that way to bring everything back to equilibrium. It's going to want to go to the right. Think about it. It always kind of goes downhill if you think about it that way. It's going to want to go, oh, well, I've got more of this. Well, it's going to go downhill to the side that's low. Oh, I have less of this. It's going to want to go downhill to fill that up again. All right, think about it that way if it helps. That's the way that I got through chemistry when I was your age. I understand a little bit more now, but when I was your age, that's how I had to think about it. So if the system is heated, that means there's more heat. It's still going to flow to the right to bring everything to equilibrium. Still going to flow to the right to bring everything to equilibrium. Now we go to D. More water is added. Okay, cool. That doesn't really impact my equilibrium. Because it's a liquid, okay, if you look back at the equation, I still have it underlined because it's a liquid. It's not really going to impact the system that much. Okay, so this is liquid water, and so we don't care. And so you really would say none here. Now, that being said, if you guys did tell me and said, oh, but if you add more water, if there's more water, that means there's more product, so it's going to shift back the reactant side to bring everything back. So if you said to the left, I'd probably give you some credit, but in reality, none is the answer that we're looking for here. All right, none is what we're looking for. All right, let's take a look at the next reaction. Hopefully this will go more smoothly. All right, so this one's less confusing. There's a whole lot less stuff going on. But there are gases now. So instead of dealing with AQ, which you guys know means aqueous, that just means it's dissolved in solution. Instead of dealing with AQ, now we're dealing with gases. So it says give the KQ expression for the reaction. I think I can probably handle that. Now I know, and you know, it's products over reactants. Products over reactants. So we can start by looking over here on the product side. Okay, and then we'll look at the reactants in a moment. All right, so we got products over on the right, we have reactants over on the left. So some of you probably thought and said, oh, well, I need to put, all right, one of the products is sodium carbonate, Na2CO3. No, that is not going to go in your KQ expression because look right here, it's got an S. Okay, we do not want to have any solids in our KQ expression. But what we do want is we want a gas. We want CO2G. We want H2OG. We want those gases. So that's what's going to go in our KQ expression. Okay, so CO2 gas, definitely going to go in. Also, remember, you need to double check to make sure it is balanced. This one is balanced. And the reason I know that is because I have a coefficient up here in the very front. So that means that someone has already done the work and balanced it for you. So what that means is if there's no coefficient in front of CO2, that means we don't put an exponent on it. Now, if it makes you feel better, sure, you can go in and put an exponent of 1. That's not going to do anything. An exponent of 1 doesn't change anything. My only other product is going to be H2O gas. And so that's going to go there as well. Once again, it does not have a coefficient either. And so therefore, we're not going to put an exponent on it. And the last thing is you're going to say, all right, well, it's products over reactants. So, okay, my only reactant is sodium hydrogen carbonate. But guys, again, this is a solid. You will not put solids in a KQ expression, so don't do it. So what that means is that right there is all there is to it. That's the full KQ expression. That's all of it. And so if that's the full KQ expression, that's it. I don't need to do anything. If you wanted to, you could do all this over 1, but nobody writes it that way. And honestly, I keep writing the little dot. No one really does that either. You don't need that dot there. You know that if two things are written next to one another, that means they're being multiplied. I just do that for your benefit so that you understand what's going on. Let's look at number 5. For each of the following changes to the system, explain which direction the reaction will shift. So for each of these, we got to predict which way it's going to go. So once again, additional NaHCO3 is added. Okay, additional NaHCO3 is added. So in that case, all right, in that case, it is still a solid. So you would say, oh, well, if I have more of this solid, isn't it going to go until it forms I mean, it's already at equilibrium. So if you add more of a solid, it's not really going to change anything because those gases are occupying the space. Think about it this way. I'm going to draw a picture for you. It's going to be fantastic. Let's assume this is all taking place in a flask. Oh my goodness, that actually turned out way better than I thought it would. So let's assume this is all taking place in a flask. Okay. When you do that, say that some of what you have is this NaHCO3 solid. All right, so all this down here, let's say this is NaHCO3 solid. All right, so there you go. It's crystalline. All right, it's crystals. They're just kind of hanging out in there. Let's say you also, when that happens, some of it is going to automatically decompose to form Na2CO3. So some of it is going to decompose to form sodium carbonate right away. So I'm going to use, I got to have something that's a little more noticeable. Let's say I use these yellow to represent sodium carbonate. So this is going to be my sodium carbonate solid. All right, so there you go. There's that. Now, when all this happens, you end up getting some H2O gas that's floating around, and you end up getting some CO2 gas that's floating around. But the thing is, if this container has a stopper in it, okay, which it now does. I've put a stopper in it. That means none of that gas can escape, none of that gas can go in. And so what that means is at equilibrium, when you have a certain amount of carbon dioxide, when you have a certain amount of H2O vapor, they are filling the container and all that empty space up there above the solid and making it so no more gas can really get there. So if you add more NaHCO3, that's great. That's really not going to change the equilibrium because the container is already filled with as much CO2 and H2O gas as it can hold in that space. So it's not going to shift the reaction. So another thing to think of, another way to explain this, it's a little more simple, that you guys will probably like better, is just like when you're writing a KQ expression, if you don't want solids and liquids, you don't want those, they're really not going to impact the way the reaction is going to shift either. So if I have more NaHCO3, that's great. That's going to have no effect on which way the reaction is going to shift. Okay. Next thing, let's look at CO2 is removed. So if you remove CO2, okay, thinking back to our flask example, if you could somehow go in and just take away some of the CO2, this is going to impact the reaction. So think about it this way. All right, we're at equilibrium. But if I start to take away CO2, which is on the product side, if I start to take away CO2, isn't the reaction going to shift in that direction to form more CO2 to bring it back to equilibrium? Yes. So if you remove CO2, it's going to shift to the right towards the product until more CO2 is formed to bring it back to equilibrium. So it's going to shift to the right. And if you really wanted to, and you wanted to say, oh, well, this is going to go to the product side, that's fine too. If that helps you, if that's how you'd rather write it, you go right ahead. Let's look at C, because this is where things get interesting. Pressure on the system is decreased. So once again, I'm going to make you guys kind of a little flow chart to explain what's happening here. Think about this. If you have less pressure, there's less stuff pushing in on it, then in general you would say, oh, well, the volume's going to increase. If there's less pressure pushing down on something, you would say, oh, well, then there's more space. So think about that. More space. More space for what, Mr. Nairn? Well, more space for gases, okay, to move around. More space for gas. And so if there's more space for gas, the equilibrium will shift towards the side with more gas. And obviously, if you look at the reaction, the reactant side has a solid, the product side has a solid and two gases. So think, if there's less pressure, there's not as much pushing it together, there's less pressure. Okay, there's less stuff pushing on it. That means there's more space for the gases to move around. And so it's going to go towards the side with more gases because, hey, they've got all this space now to move around. They have all this room to go around. So it's going to shift to that side. So in this case, it will shift towards the right. And once again, if you're saying, oh, well, I just want to say it shifts to products, you can, but it's easier to just think left, right, none. Now let's go to D. The volume of the container decreases. So once again, I'm going to do this in a flow chart. So think about this. If volume decreases, then what that means is we're taking a container and we're making it a smaller container all of a sudden. So I can't do that. This is filled with water. But a balloon is a good example. You can take a balloon and you can push it together so that you decrease the volume. You can make it so you squeeze it together more tightly. So if you decrease the volume, that's probably going to cause an increase in pressure. But what's more important is not just that. If you have a decrease in volume, that means there's less space for gases. There's less space for gases. So it's going to shift towards the side with less gas. And so obviously, if we look at our reaction, the side with less gases is the reactant side, which is on the left. So it's going to shift left to go to that side. Because again, when we're talking about volume, you can think about it like this. Here's the volume that it would normally have. Okay, let's say that's it. But now if we decrease the volume, see, there's a lot less room for gases to move around. And so it's going to have to tend towards the side with less gases because there's not as much room for the gases to be in the container. So it'll go back to being a solid, for instance. Okay, maybe it'll precipitate and become a solid. All right, so that is this activity. And guys, I'll have to admit, equilibrium is weird even when I teach it in person. When I was teaching it last semester, it was weird and annoying back then. It's even more weird and annoying when I have to do it digitally and I can't work with you one-on-one. If this were in a regular class setting, we have a whole game that we do with this where we have left, right, none, and we do it as a class. We don't really have that ability right now, so this is the best we can do. So understand, take it this way. I have now gone over the KEQ worksheet in its entirety. I have now gone over Unit 5 review in its entirety. And now I just went over the key to the quiz that I gave you last Friday. All of it. So you have as much information as I can give you. Try. Do the best you can. Get this stuff copied, but I hope you're listening and trying to understand where I'm coming from. Whether you want to think about it like a seesaw, whether you want to think about it as two beakers with a tube in the bottom, and if you add water to one beaker, it's going to flow down the tube to the other one. I don't care how you think about it. Do the best you can on this. Don't freak out. Your test is tomorrow, and just like the last test, you can take it as many times as you want. I just want you guys to do the best you can in these extenuating circumstances. So tomorrow, a lot of stuff is going to be due. Make sure you're doing what you're supposed to. You're submitting where you're supposed to. If you are having issues with technology, please call the Technology Help Center. That information's on Google Classroom. They would love to help you. They've been extremely helpful to every student that's called them. So if you're having issues, talk to them. And the reason I'm saying that, students, is tomorrow's a due date. And I know what some of you are going to do. You're going to wait until tomorrow, and then you're going to be like, oh, my OneNote's not working. Sorry, Mr. Nerd, I couldn't turn it in. My OneNote wasn't working. No, I'm telling you, it will work if you get help from the Tech Center. So please, I've said it on my Google Classroom a couple of times. Find solutions, not excuses. Try and find a way to do your job, which right now is a student, okay? And do the best that you can with that. All right. Emily, are you talking about, let's see, problem number 2 on this, where you just do the math? Is that what you're talking about? Because if so, I can definitely help you. There's a couple different ways that you can do it in your calculator. So I hope you understand where all the numbers came from. I tried to color code it the best I could to show you. I'm just plugging in numbers where they belong. And the thing is, the problem lists it in a certain way to try and confuse you. See, they don't list it in order. They don't do products first and then reactants second. They do reactants first and then products. So kind of look at what I did in 1 and 2 right here and try and see how I color coded it. So the blue goes with this cobalt chloride. The yellow goes with this cobalt hexahydrate, and then this 0.25 goes with the chloride ion. So everything goes where it needs to. But if you're only concerned with what happens in the calculator, well, here are 2 ways you can type it in the calculator. So here's way number 1. Here's way number 1 in the calculator. And it's parentheses. I really like using parentheses. I think they're great. They help with order of operations when you're typing things in the calculator. But you've got to be careful with how you type it in because you don't want the calculator to do the wrong thing. So one way to do it is I'm going to put parentheses around 0.60. Then I'm going to do my divide symbol. Let me scoot over a little bit so you can see this. That'll work. Then I'm going to do parentheses again. And I'm going to do 0.5, close parentheses, oops, no, not yet, times, parentheses again, 0.25 to the 4th, close parentheses. So the thing is, I've got a couple different parentheses here for a reason. These parentheses right here that I'm going over in purple are there just so that your denominator is kept separate from your numerator, because otherwise what will happen is it'll do 0.6 divided by 0.5 times 0.25, and that is not at all what we're trying to do here. So by doing it this way with these purple parentheses, try saying that 5 times fast, is it makes sure that it does everything in the denominator first, then it does 0.6 divided by that. So that's one way you can do it. The other way that you can do it, and this is the way I did it in practice when I was going through it the first time, is I started by just doing the order of operations myself. So instead of trusting the calculator and trusting the parentheses to do it, I did it myself. And it took several different lines in the calculator. But first thing is I said, all right, well, I started by doing 0.25 to the fourth. And then I hit enter. Okay? And when I did that, it spit out an answer. I don't remember it off the top of my head. 0.0039 and some other numbers. So it ended up giving me that on my very next line. Then what I said is, okay, well, times, and when you do that, it already makes it an answer. So on my next line, as I said, answer times 0.5. Because that's what we did in the reaction. We're doing 0.25 to the fourth. Check, we've done that. Then we multiply it by 0.5. And then I hit enter again. And I got 0.00195 is what I got. That's not the answer either. Right now, what I've done, in fact, if I were to stop right here, is literally what I have is I have 0.6 divided by 0.00195. That's what I've done so far. So obviously, the last thing I need to do then is in my calculator, I'd say 0.6 or 0.60, if that makes you feel better, divided by second answer. So literally, you have to type in second and then the answer key somewhere on your calculator. Or, hey, if you want to, you could say 0.60 divided by 0.00195. It's just that by doing 0.60 divided by answer, it gives it to you without you having to retype in that number. But anyway, I hit enter after either of these, and that's when I got that 307.2 number. Okay, so that's how I did it. So there's two ways that you can do it in a calculator. I know it's kind of weird and there's a lot of stuff going on, and it can be more confusing when you have multiple exponents, but that's how you do it. Okay. Any other questions from the two people that are here? We are at the Q&A section of the video, and now everything's working fine. So if you have any questions, please ask, and I will do my best to answer them. Give you a minute before we get off. We're keeping this one kind of short. I gotta post something on Google Classroom that I forgot about because I'm a bad teacher. Let me know if you guys have any questions. I'm here. Give you another 5 minutes, or no, not 5 minutes, 30 seconds. And if nobody says anything, I'm just going to end the stream and do some other work I need to get caught up on. All right, guys, thanks for tuning in. I'm going to go ahead and end the stream. If you do have questions, you can comment on the video, but it would be better if you just sent me an email, or better, send me a remind text. Remind texts are about as quick as you can get, and it's really helpful because I can write something down on a piece of paper and take a picture of it and send it to you. So if you have questions, you know where to find me. Hope you guys have a great day. Gosh, that was pitiful.